In section 10.6, we cover cylinders and quadric surfaces. Quadric surfaces are essentially something like the quadratic curves that we learned in algebra classes before this. So we actually looked at that possibly in a trig or pre-calculus class and a little bit in Calc 1 as well. Anyway, this is the three-dimensional extension of that. The first thing we see are cylinders. First thing we see are surfaces, to be more precise there. It's an equation involving three variables. It'll describe some sort of contoured plane. Imagine you take a plane and warp it into these different shapes, then you're forming a surface. Surfaces are the same things that we found the volume of in Calc 2, if you recall doing that. So a cylinder is one of the most simple surfaces we can design. So let's zoom in with this cylinder on the left. And that's literally a cylinder. What any cylinder starts with is some plane curve. Here's our plane curve right here in blue. And now we extend that plane curve. If we imagine we extend this circle up all along the z-axis and all downward along the z-axis, then we would form, well, a cylindrical shape, and the surface is this the outside of the cylinder that we're seeing, or that's what looks like a solid. It's not actually a solid, it's hollow. So that's the only idea with that. We've got all the lines that pass through this bottom curve right here. So here is one of the ruling lines of this plane curve. Here's another ruling line, and then all the arrows we previously drew more or less represent a ruling line, or a ruling. Here's a ruling if it's on the surface of that cylinder. It passes through this curve, that's the most important part, and it's one of the lines that makes up this cylinder. Okay, a little bit less obvious for a cylinder is to take perhaps some sinusoidal curve. This is on the left. Again, we'll start with this as our plane curve. Maybe it's sine of x, or it doesn't look like it could be sine of x, but it's some sinusoidal wave. It's in the xy plane. So let's denote that. Remember that this is x and this is y. And if we extend it up and down along the z-axis, that's what all these ruling lines here are doing for us. Right? They're forming a line that passes through this curve here, and it forms this sort of curtain shape along the rest of the three-dimensional space. And of course it continues indefinitely upward and indefinitely downward along all of these ruling lines. So the book has some really nice pictures of this. One thing that this picture over here might look a little bit like, or might remind you of, should be a corrugated tin roof, sort of a wavy looking roof that might go on top of a shed or something like that. But if you look at a picture in the book, or the pictures that they have in the book for this section, you get some clearer images of what's going on. But the key idea to a cylinder is you start with a single curve in a plane and then extend a bunch of lines through that curve. So let's move on and have a look at quadric surfaces. There's a little bit more to these. So a quadric surface has the general form, or its equation will have a general form, which looks more or less like this. Sometimes you'll have to complete the square or do some factorization work to split these things up into more recognizable forms and be able to determine what kind of surface you're actually looking at or dealing with. So let's have a look at maybe the basics of all this. We're given a surface z equals y squared plus x squared, and we're asked to graph the surface using traces. So a trace is essentially you shut down one variable or fix one variable of the three and draw what the resulting curve would be. So if we look at just the z values from here, counterintuitively we're going to say let's fix our z values in this equation. Well, if z is equal to 0, well then x and y must be 0. So just to start with 1. And that actually gives us the origin, 0, 0, 0. When z is equal to 0, y equals 0, and x equals 0, this equation is satisfied. So the origin, 0, 0, 0, is on this curve, or on this surface, rather. Okay. Now, a little further, what happens for positive values of z? Well, suppose z is equal to 1. Well, then that leaves the equation as y squared plus x squared equals 1. Pretty obviously a circle. It's centered around the origin, or in this case, the z-axis. So we draw it down here. There's our circle with center being the z-axis and height being at 1, z equals 1. So it's living in the plane z equals 1. And as we move upward, we can draw more circles that are similar to this. When z equals 2, that's a circle that's just a little bit bigger radius, and so on and so forth. This isn't exactly z equals 2, but it's approximating some upper planes above this xy plane. So it's showing that these circles will just increase as we move upward. Okay, when we look at the side of this, if we were to imagine fixing x, so if x was 0, then z equals y squared is the resulting equation. This would be a parabola. This would be this parabola that we see right here. Okay, now if y was 0, then z would be equal to x squared, and we'd have a parabola in the xz plane that would look something like this. Right, so that's flat coming out of the page at us, if you can imagine that. So it's parabolic on all those traces, but the circles really kind of do enough for us. But we complete the outside of it with this, and we just assume that the one that we drew previously is in there as well. Okay, so this will be called a paraboloid as we get to know these surfaces. And there is a classification coming up right about now. So we can classify all of these surfaces based on getting them into a standard form that looks like something on the right-hand side right here. Okay, so the idea then is to get it into a standard form and classify it. We can still use traces because we have some idea of what these things should look like. If we look at, an ellipsoid, it might look somewhat like a football, or maybe more accurately a rugby ball, if that means anything to anybody. So there's an ellipsoid, sort of a squashed ball or squashed sphere. An elliptic paraboloid. So we take a paraboloid, which was circular in the previous one, and then we can really flatten out its opening or flatten out its sides. Do something like this. This would be sort of a flattened version of, a more round paraboloid. Okay, more circular paraboloid. So there's that one. Hyperbolic paraboloid. This one's a little bit harder to draw, but this essentially looks like a saddle. We have a hyperbola going flat on the page. We have one coming in and out of the page. To draw this is a little bit tricky. And this is the saddle shape that we'll have here. We'll see a graph of one of these in just a bit. So that's the hyperbolic paraboloid. A cone is pretty straightforward. A cone would just look like something like this. That would be this equation given right here. Okay, continuing. Or it could be elliptic, right? That's one thing to note about the cone. It could be an elliptic situation. Rather than having a circular opening here, it might have an elliptical opening there. It's hard to represent that in a quick sketch. Now, further, hyperboloid of one sheet. So that would be a hyperboloid that's joined. Nuclear power plants, the heat stacks on a nuclear power plant is actually a hyperboloid of one sheet. Something like this. Could be elliptic at the top or circular. And we have this situation here. Now the last one is a hyperboloid of two sheets. The hyperboloids have pulled away from each other, and they're pointing kind of like paraboloids, but they're pointing away from each other and they're separated from one another. So they're all analogous to their two-dimensional counterparts, the hyperboloid and the hyperbola, and so on for the rest. But let's have a look at actually classifying one of these and getting an idea of what these things might look like without just referring to the table, which is an important skill here. So we're asked to classify the surface given by the equation. Okay, maybe put it in a more standard form. If we have a variable that is not squared, is y, it makes sense to solve for it. For one reason, you can go up to the table if it's handy, and you can find something that looks more or less like that and get an idea of maybe what this thing is. But it also just makes this process a little bit easier in general in terms of classifying it without a table. So if we fix y greater than 0, what are we left with? That produces, say y is equal to 1. We'll just choose an arbitrary value, but any positive number would be fine. And when y is 1, this is an ellipse. 4x squared plus 2z squared equals 1. The weights of x squared and z squared are not exactly the same. In other words, their coefficients are the same. So we know that this is forming an ellipse, weighted one way or another. And it's an ellipse in the y equals 1 plane. So it's hovering above or hovering next to the xz plane there. Okay, so we're an ellipse one way, in one slice. If we slice it the other way, set x equal to 0. When x is 0, we get y equals 2z squared. That's a parabola in the yz plane. Okay, so we have a parabola in the yz plane. When z is equal to 0, we have y equals 4x squared. That's also a parabola in the xy plane. So two slices of this is a parabola. Another slice is an ellipse. The third slice is an ellipse. So this is a paraboloid. An elliptic paraboloid is what we might call it in general. So, and we could also check with up above. This form right here is exactly the form that we have in our case. It's just that c is equal to 1. And, well, okay, we've swapped the role of z and y. That just rotates what axes we're on, or swaps out which axes this thing is aligned with. So elliptic paraboloid for this one, and that's just by imagining what this thing could look like. Geogebra is a nice, or any other 3D graphing tool can help out with these things as well. But I really encourage trying to figure out what each of the slices is down here, and being able to put together what that picture should be. If it's a parabola in two different planes, then that means it's this sort of 3D surface parabola. And if it's an ellipse in a third one, then that means that the opening of that 3D paraboloid is elliptical. It's a nice way to possibly see all that. Okay, now classify the quadric surface represented by the given equation and sketch its graph using traces. So classify and sketch it. Use traces if you can. In this case, this one's really hard to graph, so we're not really going to try to sketch it by hand. But we do the same thing. Using traces, we fix some values that make sense. Z equals 1, we end up with this equation. That's a hyperbola. Y squared minus x squared equals 1. You remember from an algebra or pre-calculus class, is a hyperbola. It contains the point 0 plus or minus 1, 1. We know that because we fixed z to be 1 anyway. And then when we plug in 0 for x, y squared is equal to 1 gives us plus or minus 1 for y. Okay, so now we have 2 points on that hyperbola. Those turned out to be the vertex points of the hyperbola, and we'll know how to sketch that roughly in the graph below. We'll do that last. So notice that we can't zero out y. If we do, we have negative x squared equals positive 1. There are no x values that will satisfy that, so no such points exist with y equals 0. So that's one thing to keep track of. That'll tell you where the curve exists or where the curve doesn't exist across an axis. When y equals 0, there's no points there that are on this surface. Okay, now moving on, we see we'll next fix y equals 0. When we do that, we have z equals negative x squared, and this is a parabola that opens in the negative direction, or the negative direction for z, or the downward direction. Now x equals 0, also a parabola. It opens in the positive direction of the z-axis, in the zy plane, and also the one above was in the xz plane. These are color-coded for the graph below. Overall, we'll say that this is a hyperbolic paraboloid. Once again, 2 ways were parabolas, so that makes it a paraboloid. 1 cut was a hyperbola. That gives us the adjective hyperbolic paraboloid. So down below, let's see an attempt at a sketch of this. This is where things get pretty hard. The first thing we sketched was the hyperbola that we found, this is actually in the plane z equals 1. So it's parallel to the xz plane, and it's flat, sitting above that at a level of z equals 1. Not as constructive as the rest of this. Now, z equals negative x squared. That's our downward opening parabola. It's on the xz plane, which sort of comes out of the page towards us. And then we've got the yz parabola. That's z equals y squared. It's opening upward in the positive direction, and that's flat on the page. So to draw more of these is really just to confuse this situation, but you can see that between these two parabolas, we have this saddle shape going on, most likely. So I've got a GeoGebra image. Let's have a look at it in GeoGebra. In GeoGebra, what we see now, so we've loaded this thing in just to be sure of it. And we've got z equals y squared minus x squared in our graph prompt to put our equation in. So that's great. But let's have a look at this thing. If I rotate it, we see, yeah,